Well, welcome. It's 2:45. We're going to start. This is live stream, so we have to use a microphone. And we have two presenters for this. One is a stroller, and the other is a stander. And so we'll see how this works out. We will not identify and out which is which.
Very good.
My name is Stephen Sprigle. I work at Georgia Tech, and this is young Dr. Jacob Misch. The most stellar postdoctoral fellow in the history of mankind. Yeah. Full disclosure, I've never met him. It's just the rumor going around. Yeah. But we're here today to talk about vibration, impact, and energy dissipation of manual wheelchairs. So these three constructs are all interrelated, okay? That means you can't decouple them. They are what they are. And some of it's a terminology issue, some of it's sort of a mechanics issue, but it all gets around energy, okay? So as we go through this, this is a talk on energy.
Those are there just for fun.
These are here just for fun. So the learning objectives are to sort of differentiate into these two kinds of energy, okay? One is vibration and the other is impact or shock, right? And then what are sort of wheelchair-specific design considerations and even wheelchair-independent design considerations that affect this kind of energy, the vibration and the impact, okay? And finally, the part y'all hate. What trade-offs, what compromises do you have to weigh as clinicians and prescribers to optimize the system according to the user and the user's context of use? Why do you hate that? Because it makes you think, and it's painful, and you deal with uncertainty. Why do I think that's good? It's because it's why you are good clinicians, because you think critically. This is way better than following a bouncing ball. Prescribing a wheelchair is not making an omelet. It's harder than that. You deal with uncertainty. So why is this important, right? It's important because of a lot of work on occupational exposure to vibration, right? And there's guidelines associated with this. And one of the sources of vibration is moving vehicles, okay? And so by extension, you have these moving vehicles and you say, oh, a wheelchair is a moving vehicle. Let's consider whole body vibration, right? And because it's occupational in nature, there's a lot of guidelines and regulations associated with it, right? That's what, we do in the vocational occupational safety world, right? In terms of a vehicle, though, this is what we're dealing with, okay? Because we're dealing with a moving vehicle. There is not one factor that dictates or influences whole body vibration. It's the type of frame. That could be the frame of the wheelchair, it could be the frame of your bike, frame of your car, right? Chassis of your car. It's also the suspension that it has. Some bikes have suspension, cars have suspension, tractors have suspension, some wheelchairs have suspension. Also the type of seat and the cushion you're on. Your drive wheels, what kinds do you have, and your diameter, and the caster type and diameter. Have you ever inflated your tires? Have you ever checked your tire inflation? How much the occupant weighs. Does that matter in a semi? Probably not. Does it matter in a manual chair? Big deal, right? And then how do they sit, right? If you come off the backrest, you have a different exposure to vibration than you're on the backrest, which is different than if you're reclined. Finally, what are you rolling over? Is there a lot of vibration in this room? And we'll talk about that and how fast you go. Okay. Now let's distinguish between impact, shock, and vibration. okay? Because they're different. Not in terms of sort of, you know, the fact that they're both energy, but it's sort of how this energy is manifested. And this gets to the heart of some of the objectives, right? So whole body vibration is sort of this stuff that's transmitted to the whole body, right? And it's sort of characterized by this sort of oscillation that gets to a mean of 0, right? It's just sort of this bumping around, and you feel it every time you ride a bike. You feel it in your car, right? Okay. And it can happen in a vehicle, but it also happens in power tools, okay? So there's guidelines associated with that, okay? How often you use a drill or a jackhammer and all that, that influences your whole body, okay? It has a risk, as we've talked about, but it also has been used therapeutically. So they use whole body vibration in certain situations because energy is being absorbed with the body that influences positive therapeutic effects, right? Shock is transient, okay? This is hitting a pothole. That is not whole body vibration, that's shock or impact, okay? It displaces the body in a much more marked way, okay? You may have to do a reactive response, right? Okay, so it's a disturbance, okay? But it's also very low frequency. You know, you should not try to hit every pothole riding your bike, okay? And so you can see it can happen anytime, right? It's a perturbation, it's a surface perturbation. But remember, it's low incidence, okay? This is not something that happens as you're, you know, driving to work all the time. Okay. So they're both energy. But designing for shock, designing for impact is different than designing for vibration, okay? In fact, when you buy vehicle seats, they can have ratings for both. And generally, they have to have different systems for both. The majority of these seats only do one well. So if you're a bus driver, you tend to go with the whole body vibration, right? If you're on a construction site doing a tractor, you may choose the shock. It's a different context of use. That's what you have to think about when you're dealing with wheelchairs and wheelchair users. How are they using it? Are they on a construction site, or are they just riding down a sidewalk? Anybody have fat tires on their bike? Nobody. Okay, yeah. Okay, so do you live with sand or snow? No. Right, okay. Why did I know this? Because that's really all they're for. Okay? Yeah, it's a soft surface, right? And I like how you distinguish between sand and dirt. That was a little geeky of you. Yeah. And so you're absolutely right. This is what they're for, right? They're designed for this context of use, right? And they do a very good job. They also add suspension when you hit a root, right? Going down off-road, right? That kind of shock. They're really good at that. You know what they're not good at? Riding down a street. There's a lot of energy loss. They're not designed for that context of use. I was in Key West with the ex-president of Resna and the godfather of my son, and he decided to rent one. Granted, the purpose of riding a bike in Key West is to go from this bar to this bar to this bar to this bar, right? He lasted about 2 hours, and he says, you know, I have to pedal all the time. I go, yeah, that's because you got this bike. Yeah. So it adds work, okay? So when you're dealing with wheelchair users, a few caveats. The guidelines you're going to hear about are for healthy individuals and probability of prevention. They are not about people who already have a bad back, okay? They're also based on occupational guidelines, meaning their time and intensity. In a wheelchair context, the most meaningful issue associated with vibration is tied to comfort, not musculoskeletal damage. And we'll make that case more than once. Comfort is individualistic. That means it's subjective. That means you have to ask people. And in comfort, vibration manifests over the body. Sometimes it's the neck, sometimes it's the shoulders, sometimes it's the feet, okay? Because it's frequency and intensity, you also have to have a chat. Remember context. Is this something you experience once a day, once a week, 3 times a day, okay? Is it minimal discomfort? Is it moderate? Does it affect your function? Because there's trade-offs involved, those answers are important because you're going to ask people to make compromises. You're going to ask people to choose. Do you want a fat tire or not? Okay. Finally, the approaches to lead to attenuation are energy loss. That's what it is. Okay? You have to absorb energy, lose energy to attenuate this. And that means it can increase propulsion effort. Is that a bad thing? I don't know. Depends how important it is to you. That's the trade-off, right? Finally, dissipating shock requires different interventions than dissipating vibration. There's products out there designed for shock, and there's products out there for vibration. They are not the same thing. All right? So, this is why we make the claim that vibration should be evaluated against comfort, not injury. So these are the guidelines, okay? This is a calculator. You can plug in numbers. It's from the UK. And you basically have these 2 limits. They're occupational things. And so you say, this is the vibration exposure, and this is where you have to take action. So in the UK, you say, we have to take action if it reaches this. And there's another level that says, you're not allowed to do this. You're not allowed to expose a worker, okay? Okay, so 2 levels. If you look at the vibrations associated with tile, brick, sidewalk, and grate, you'll see the amount of hours of accumulation that it takes before you have to even worry. There are 24 hours in a day. So when you see a 24, it's really not going to happen. There has never been anything associated with Americans that says we either walk or wheel a chair 14 hours a day. Maybe a postman back in 1965 did 6 hours, I don't know. But they ride now, right? Mailmen ride, mailwomen ride. But that's a long time, okay? That's the caveat. This is really a comfort issue based on the science, the guidelines, and the measurement. Doesn't make it less important, it makes it different. Next up, bunch of data and some physics. And a stander, not a stroller. Are you really going to stroll? Well, yeah.
That doesn't actually show the the screen as it happens up here. So I'm going to stand over here. I might walk all the way over there and help out the people on that side of the room too. But thank you, Dr. Sprigle, and thank you all for being here. I want to preempt my part of the talk by saying I'm an engineer. I think, I talk, I present like an engineer. That's going to be evident in like a slide. Don't worry. But that being said, if anything catches your interest that warrants a follow-up, a clarification, a discussion throughout the rest of the slideshow, don't be afraid to ask questions. Come up and find us and talk to us. I want more than anything to make this data, which I really like talking about, actually relevant and, oh, there it goes, relevant and interesting to the clinic, to wheelchair users, and to manufacturers. So now I'll get into more of the fun stuff from me. I want to go through some of the tools that we can use to assess whole body vibrations, the complex ones and some simpler ones, and then talk about some of the tools that we've established to measure whole body vibrations. And then I'll go through some studies to answer these really important questions to me. First, are wheelchair users exposed to harmful vibrations? Second, are there components out there on the market that reduce the level of vibration exposure? And third, do different frame materials, specifically carbon fiber and aluminum, do they differ in how much vibration reaches the user? Would you have access to the slides? I believe so. Yeah, once we get there, yeah. Two of the studies that I'll be talking about are already published. The third is hopefully well on its way. Oh, perfect. All right, stepping foot into the whole body vibration territory. Like Dr. Sprigle was talking about, whole body vibrations are unavoidable. They don't always happen because you're running a jackhammer, you're sitting in an excavator. You experience them when you're riding down the street in your car, when you're on your exercise bike at home or in the gym. They're especially bad when you're in a seated posture, where the vibrations traveling up through whatever you're sitting on travel directly up through your spine. Right? So the prevalence of lower back pain, neck pain, shoulder pain, whether they're caused or just exacerbated by these vibration exposures, the correlation's there, right? And of course, when you're talking about wheelchair users who are in a seated posture all day, every motion they make in a chair inducing these whole body vibrations could go towards that lower back pain, neck pain, shoulder pain. So our big question here is, are wheelchair self-propelled travel-induced vibrations, are they harmful, right? So I'm going to start by talking about some tools that are already out there to assess whole body vibrations. The first comes from the International Standards Organization, ISO 2631-1. Now this was designed predominantly for use in the workplace. So looking at able-bodied seated employees sitting on industrial machinery for 4 to 8 hours per day, right? Unfortunately, these are limited assessments to the workplace, so it doesn't factor in your commute to and from work or the recreation you do once you get home, right? But in general, ISO describes this data flow. So when you start wanting to assess whole body vibrations, you first start by taking an accelerometer, this chunky blue device in the bottom left corner, and placing it under the user on top of whatever interface is between them and the equipment that they're using. So whether you're hollowing out the cushion that they're sitting on or just placing it directly under them, you're measuring right at the interface. And this plot in the top sort of shows you the spiky vibration that the folks are exposed to. ISO recommends using a series of filters to cut out some of that noise and reduce the high and low frequencies and really zoom in on the frequencies that are shown to affect human tissue. You do this for each individual access, so the fore, aft, the lateral, side to side, and the vertical directions. And so you get 3 different time series of data, right? And then, again, being an engineer, I like the equations up on a slide, but don't worry. For general whole body vibrations, you're just taking almost like a running average. It's a root mean square. It's a function in Excel. So if you have a big column of data, equals RMS, that column of data, and you get a value spit out. If the data also includes, or you believe it includes shock or impact, there's a different, a little bit more complicated equation that involves not just square roots and raising, squaring the number, but raising to the 4th power, right? A little bit scary even for engineering folks. But then you take that singular value and you compare it to some guidelines or limits or thresholds put together by ISO or other regulatory agencies. So to go into a little more detail about the filters, just so you understand what they're trying to get at, you generally want to focus on what is harmful to the human. You don't want to just capture anything. You don't want to capture the 60 hertz signal just because you're next to a power line, right? So you want to cut out frequencies that are below a certain limit. So if something takes, 4 seconds per oscillation in your signal, get rid of it, right? The human is mostly not affected by that signal. You're also cutting out anything over 30 hertz, and you're really zooming in on this 4 to 12 hertz frequencies. That's what affects the human tissue. That's what causes the lower back pain, neck pain, shoulder pain, based on studies in the workplace, essentially. Then at the end of that data flow, right, once you get that singular value, that golden value at the end of the data pipeline, you can compare it to this plot here. So this is ISO's attempt to make it really easy to assess what vibrations you're exposed to. On this vertical axis is your vibration value, and on the horizontal axis is your exposure duration. So you also see a couple lines plotted across these across this plot, and those are thresholds, right? So if you're above the top threshold, you're basically in a zone where you're exposed to a lot of vibration for a lot of time, right? This is sort of the danger zone. It's where risks are known to occur associated with whole body vibration. If you're below the lower limit in this green zone, that's where no known risks exist. So you're pretty safe if you've got these low magnitude vibration exposures for even long-term exposure throughout the day. And everything in between in this gray area is this caution zone where you're advised not to be in, right? Either reduce your vibration exposure or your duration to get back down to the safety of the green zone, right? Long-winded buildup, but here's an example. If you're exposed to 1 meter per second squared of vibration per day, you just take your value and you plot a line across this plot, right? And you take a look at where it crosses these thresholds. So you travel all the way to the right until you reach the gray area at about 1.5 hours. So anything below 1.5 hours of exposure at this level, you're safe, right? If you keep following the line across, figure out where you cross into the red zone at about 6 hours, that's where it becomes a known health risk and you're putting yourself in danger of injury. Everything in between, you're just advised to kind of watch your vibration, try to minimize as much as possible. All right, if that was a lot to take, trust me, I know. It took me about 3 months to interpret all that and build code to try and, make heads or tails of our data. Don't tell my boss. But there are also tools that simplify this assessment. So like Dr. Sprigle was talking about, the UK put together with their health and safety executive a calculator to just plug in your values, and it tells you how long it's going to take to reach harmful or cautionary levels, right? And they put a stake in the ground saying that if you're exposed to 0.5 meters per second squared of vibration over an 8-hour day, that's about how much you should be exposed to at max in the workplace. Anything over that, it's the employer's responsibility to either reduce your hours to that machine or reduce your vibration, give you some better cushion, for example. And anything above 1.15 meters per second, really high vibration exposure over an 8-hour day, you're basically guaranteed to get some sort of injury or pain, discomfort. And so to put it in simpler terms, anything below the EAV, this action value, you're fairly safe. Anything coming close to the ELV or limit value, you're in danger and you need to take action to reduce your exposure. So the general guide here to using this HSE, Health and Safety Executive calculator, is to take your measurements, right? Put your accelerometer on the seat and measure over the duration of exposure, however long someone is actually using that equipment. And then do the same analysis, do the trimming, do the filtering, make sure you're really honing in on exactly where that vibration exposure is occurring. And then plug in that value directly into this spreadsheet. And what it gives you in this far right sort of bluish section is how long it's going to take, how much exposure you can put yourself, expose yourself to before it becomes dangerous, right? Very easy, very simple. Yeah.
You may be getting this, but is there any research to say if distributed under could impact the body exposure? Like if you're suggesting stop at an hour and a half, is that vibration still in the body and diminishing over the next 30 minutes? You see what I'm saying? Is that question?
So the question is,
Is there continued impact to the body post exposure? Just as you get off the
right.
machine, is there still an impact to the body
So my understanding of the standard and the research that the standard is based on is as long as the exposure stops after that duration, right? Say you're exposed to whatever that 1.5 hour limit was. If you stop right there and aren't exposed to any more vibration the rest of the day, you're still safe, right? That's how they get those guidelines, how they get that timing.
Complicating a little more, this is about cumulative, trauma, right? So if you sit in a truck for 9 hours and get exposed, that's not the issue. The issue is when you drive a bus for 15 years or 10 years. So it is very occupationally, this is not a one-off, right? They have done work on one-offs for shock. Is there any trauma due to shock? And it's generally no, but it can be. There has been no one-off for vibration exposure. It's cumulative.
Thank you. Now, moving into the studies. So we wanted to figure out how to apply this health and safety executive to wheelchair use and figure out what levels of vibration exposure wheelchair users were experiencing throughout their day-to-day activities. We wanted to take a mechanical assessment approach and try to streamline as many things as possible and hold control over as many variables as possible. So we wanted to use one wheelchair configuration, one frame, one set of casters, wheels, and find one occupant that was able to propel this chair over countless surfaces, countless times, exactly the same each time. Very hard to do, very tricky to find a subject like that. And we wanted to test over 4 common, sort of everyday environments with varying surface roughness. So we started by choosing our default configuration, just one ultra lightweight aluminum wheelchair frame with standard components, a spoked wheel with a pneumatic tire, a solid caster, and then a rigid aluminum fork. We wanted to test, like I said, over a couple common environments, a couple surfaces. So we chose, obviously, smooth linoleum tile. You see it everywhere you go into a company, business, hospital, school, as well as sidewalk with some big paving stones and relief joints in between. Less common surfaces, potentially. Decorative interior brick, but it had a very nice grout line in between them with a nice repetitive bumpy surface, and some expanded aluminum grates, typically only seen in an industrial workplace, basically, but a very randomized vibratory surface, right? We instrumented the chair with everything we had at the time, a whole bunch of accelerometers strapped all over this thing, trying to figure out what the vibrations looked like, not only at the seat, but right under the seat on the cross member, right? At the drive wheel axle and right above the casters. Unfortunately, we don't have time to cover all of that, so I'm just going to focus on the seat, so basically representing what the occupant would be experiencing during these travels. And then this is our perfect test subject. We struck out trying to find one person that would propel the same way every single time, so we said, we'll build one. This is the anatomical model propulsion system. It's a robotic wheelchair propulsion device that can sit in any chair, just straps its hands to the push rims, and then drives the chairs with a very repeatable and controllable propulsion trajectory. You can see the nice little video here. That's the straightest it's ever driven, actually. It's fantastic. But we gave it this propulsion characteristic of taking 2 push strokes to accelerate the chair up to a steady state speed, around 1 meter per second, and then 5 other pushes to maintain that speed, and then just let it coast all the way to the stop. Here's an example of the amps testing over the brick surface. And one more over sidewalk. I think these are a little slow because it's way harder to keep up with the amps than it looks like in this. But what did we find? So with this repeatable propulsion system, driving over these different surfaces, picking up the vibrations that the chair itself was transmitting up until the top surface of the cushion, we found that generally speaking, we're down here in these regions on this plot that I showed you earlier. Going over tile, we had vibration exposure of about 0.18 meters per second squared, right? So I plot this line on the caution zone plot and find that it never even intersects with either of the thresholds. So by the time you reach 24 hours of continuous travel, you're never even in that gray area, that caution zone. The other three surfaces are a little more grouped up at 0.36 meters per second, about double what you'd feel on the tile. But if you plot that line and follow it across, you see it only intersects with one of these thresholds at about 14 hours. So 14 hours of continuous travel in one 24-hour day to get to a place where you should be a little bit concerned about vibration exposure. Keep in mind that the average wheelchair user is self-propelling for about 1, maybe 2 hours a day, at least in the US. So again, it takes about 14 hours of travel to reach potentially harmful levels. And for these studies, even with the sidewalk, the brick, the grates, there were no shocks that were high enough to warrant additional shock or impact investigation. So even hitting those relief joints wasn't really shocking the system as you'd expect. And to put it into perspective, riding the train or the subway, much higher vibration level. And if you ride a high-speed rail, you're about 10 times the vibration exposure of a wheelchair traveling over ground. So now that we know what the health effects are, or the lack thereof of health effects, we can assess, are there any energy dissipating components out there that actually tackle this problem of vibration exposure? Do any of the components on the market reduce the vibration that reaches the person? So we use the same setup, the same wheelchair, the same surfaces, the same speed, the same robotic system, but we swapped in a few different caster and drive wheel options. And these are the options that we selected. So for the casters, we selected one different fork. This is a frog legs suspension fork with an elastomeric wedge in between where it connects to the frame and connects to the caster wheel. We chose a soft roll caster, kind of a wide, compliant material. And for the drive wheels, a soft wheel with these damper-like spokes, loop wheel with these leaf spring style spokes, and then a mountain wheel. So just a 2-inch wide, rugged, low pressure pneumatic tire. And I just like showing off the amps. So here's another video. But this is the grates surface that we're testing on. Dr. Sprigle, don't look, but at the end of that grate is like a 3-foot drop off. So that's why the video is cropped exactly there. You can see the panic in my undergrad's eyes as it's getting closer and closer to the edge. So to put this in perspective, we had 6 different configurations, 4 different surfaces. We took 20 trials on each surface. So AMPS was running 20 times on each surface for each chair. And we had 3 different measurement locations. So that's 480 propulsion trials that, say, a human subject would have to consistently propel 480 times. And it resulted in nearly 1,500 vibration files that we had to analyze. It's a lot of data. It took a long time to get through it all. And again, for the purpose of this presentation, I'm just going to focus on the seat, so what the occupant actually feels when they're traveling over these surfaces with these different components. And here's the general overview. Not all of them are very ideal at reducing this whole body vibration. They may have some benefits elsewhere, such as reducing shock and impact from reaching the user, but for whole body vibration, these are the outcomes. Right? Frog legs actually, these suspension forks increase the vibration exposure at the seat. The mountain wheel, soft wheel, didn't really have any differences at the seat. The loop wheel increased vibration, soft wheel decreased vibration. So let's dig in a little bit. So the suspension forks, like I said, increased vibration, about 16 to 25% over the more aggressive surfaces, and almost doubled vibration over tile. Why is that? What we think it could be is that the taller forks put the seat up much higher, and the deformation of this elastic wedge insert, every time you push or move around in the chair, can actually cause a sort of pitching moment. So you're tipping back and forth at the seat. And it deforms with every single push. So in terms of whole body vibration, it doesn't necessarily help the person. In terms of shock and impact, that might be a different story. It also might not be well aligned with the obstacles because this wedge is sort of directional. When you hit a door threshold or climb over the different bumps in the brick, that vibration might travel up and not travel through the elastomeric wedge the way it was intended. Next, the soft roll casters decreased the vibrations or attenuated some of the vibrations by about 7 to 10% over all the surfaces. And the reason for this, I believe, is that these wheels deform radially. So they're very, they're not reliant on a direction like the elastomeric wedge or the shocks or the leaf springs. So no matter where you hit the bump, no matter what direction it's pointing, it's going to absorb that energy as it rolls and overcomes that obstacle. It's also pliable and has a wider contact patch than the standard default casters. And the mountain wheels, this one's hard to describe because at the seat, there's no significant change in the vibration, but the perception, the user perception, is that it's a bumpy ride over things like tile. It smooths out completely fine when you're going over, more aggressive surfaces, sidewalk, grates, bricks. But you feel that tread when you're traveling over tile, even though it doesn't increase that whole body vibration value that we see. So it's all about perception at that point. The loop wheel springs, these leaf spring spokes, did increase the vibrations, 4 to 13% over all the different surfaces. I believe this to be a little bit of a combination between the directional spoke-based design and the fact that they're springs, right? They're absorbing some of that energy and then they're giving it right back, potentially in a different direction than you experienced it in, right? And the soft wheel, sort of, I suppose as expected, had mixed results. But in general, it did have a reduction over brick, tile, and sidewalk. It did attenuate some of that vibration. It just didn't help on grates. So again, a very directional design, and it's designed to absorb energy by squishing these shocks down, these dampers. So I do want to take a second to talk about a trade-off here. If you design with these deformable elements, every time you push it, you're deforming those elements, right? You're spending some of your energy to compress that damper. So there may be some outcomes where you have propulsion efficiency trade-offs with your vibration and your shock absorption. So I'm just going to put all these prices up there, and in terms of whole body vibration, you really need to decide, are they worth it? If you're talking about impact or shock, it might be a different story. If you're talking about user comfort, that comes down to user perception. But in terms of whole body vibration, this is what we found. So now I'm going to jump right into the last study. We wanted to assess how aluminum versus carbon fiber could affect how much vibration went through a frame and got to the top of the cushion into the user. Right? We wanted to do the same type of testing, but streamline it a little bit and only focus on one surface, bricks, and use 3 different aluminum frames, 1 carbon fiber frame with the same exact components on each one. So these are the frames that we tested. We chose a Key Rogue, a Quickie Nitrum, and a Motion Composites Apex A for our aluminum frames, and 1 carbon fiber frame, Motion Composites Apex C. Each one we place the robot on identically. Same components, same drive wheels, casters, tires. The mass was fairly similar across all of the loaded configurations, and the weight distribution, sometimes we had to shift some weights within the robot to get that weight distribution to be about 70% over that rear axle. But for the most part, we didn't ever add any weights to the system. So this mass range is exactly what we measured. And the general outcomes, aluminum and carbon fiber had similar seat vibration exposure levels. This is combining all three of the aluminum frames collectively. So instead of breaking it out by quick heat, key, motion composites, just all aluminum versus all carbon fiber. Interestingly, well, first, none of these measurements actually exceeded any of those safe values, right? We're still well within that green region I was talking about. It would take about 1.2 or 0.9 meters per second squared to reach any potentially harmful levels at the duration of wheelchair use throughout the day. And we're less than half that with all of these chairs. They're all perfectly fine. But interestingly, when you break up the aluminum chairs, individually assess them, you get a very different trend. You get very disparate performances throughout the aluminum frames. And so there may be a bigger discussion than just carbon fiber versus aluminum. It might have to take into account what are the differences between these frame designs? Why are some aluminum frames performing much better than other aluminum frames, for example, in terms of whole body vibration exposure? And then we did have the opportunity to have this paired comparison, this paired assessment between the two Motion Composites Apex frames. They were designed with the exact same frame angles, seat angles, again, equipped with identical components. And so this is as true as we can possibly get to just having an isolated frame material test and comparing their vibration exposure levels. You can see there is a difference, right? The carbon fiber has significantly less seat vibration exposure by about 11% than the aluminum frame. So the material can matter. But again, going back to this plot, there's such a disparate vibration exposure level across different frame designs that I'm not sure we can just look at this one plot and say carbon fiber is always better. I think I basically covered everything there. So some general takeaways. We had 3 different studies looking at question 1, are wheelchair users exposed to harmful levels of vibration? Our findings suggest no, not at all, right? It takes 14 hours of continuous travel. Even an active wheelchair user might only be self-propelling for 2. Question 2, are there components that reduce the vibration exposure level? Yes, they do exist. Not everything that claims to reduce vibration level will, but there are trade-offs associated with that. Maybe they're better at shock absorption or propulsion efficiency. And question 3, do frame materials affect vibration exposure level? Yes, but frame design is also a key factor in this vibration exposure. So this is where Dr. Sprigle was getting to with personal preference and comfort, may be the deciding factor. Since there's no health effect for any of these, maybe it does come down to what the user prefers, what they're comfortable with, what they enjoy using. I'll pass on to questions.
Thank you. So it's especially related to the first part of your presentation. The damage thresholds and the accumulated damage thresholds are normally benchmarked over a whole healthy population which have normal functional capabilities, which we don't see obviously in the wheeled mobility population. So is there any way you can take additional considerations over there?
I think we'd like to. I don't think
the data is missing, probably.
Yeah. There should be a standard for wheelchair users that's different from an able-bodied employee in an industrial workplace. Different outcomes of the same exposure level, probably, right? We just don't have that data. We don't have that standard in place.
So human variability is not unique to disability, right? And so these occupational guidelines cover people who weigh, 60 kilos or 90 kilos or 120 kilos. And some people are, 6.5 and others are 5.6. So you're sort of hosed in that way. So I never quite know what is meant by, assigning disability to a biomechanical thing, because I think it's different if you have osteoarthritis than it is if you have COPD or, some heart condition. I don't know. But you're absolutely right. Anytime you deal with a subpopulation, cumulative issues can have an effect. Whether they have an order of magnitude or more, there's absolutely no way to tell, but there's no, I just don't know exactly what you would look for. I'd look, remember, osteoporosis is one of the reasons people use whole body vibration. And that is because they assumed it would be more damaging. It's not. It's therapeutic. It's kind of counterintuitive. I think they have it for something else too. I think tone, right? Tone? Yeah, that's whole body vibration too, right? Have they done that in adults as well as kids? Yeah. We've decided to throw the microphone at people to dissuade them from asking questions.
Thank you for the interesting presentation. I have a question also about the thresholds. ISO standard 2631 is originally based on occupational diseases of the lumbar spine. So what means the values we see here as critical values are based really on lumbar spine diseases. When I look here on many presentations, the main focus is on tissue, but not on intervertebral discs. So is it really the right value to look on that setup, which is defined on the lumbar spine, and everyone else is looking here on the tissue? And did you make any measurements of changes of the pressure distribution when you see that? So it could be that you are below the level of the threshold, but still have significant increase of the pressure distribution.
So the question concerns, there's an inherent difference between how energy is transmitted in the skeleton versus in soft tissue. And of course, soft tissue dampens that energy and the skeleton transmits it, right? So your question is, you're saying that these injuries tend to be because things are transmitted through the skeleton, which is true, right? Now, the soft tissue injuries with cumulative stuff, though, tends to be more acute because it is tendinous, right? It's ligaments and tendons. Is that what you're talking about? Are you talking about adipose tissue and dermis and epidermis? Okay, you say everyone here is looking at the tissue below. Who's everyone here? Because it doesn't include me or him. So everybody but him and I, or who's everyone? Uh-huh. Yeah.
Many of the people, I'm sorry. I'm sorry. Many people are looking here on the pressure distribution, but these values are more focused on the discs.
Oh yeah, we did not measure that. The AMPS doesn't have soft tissue. But knowing a little bit about how energy is dissipated, I think you'd be hard pressed to see a lot with the distribution on a micro level. I don't even know. You will see, obviously, like when you walk, you get up to 1.2, body weight. You don't quite see that, but we couldn't measure it because the AMPS has a concrete butt. Yes. Who owns the mic?
I do, yes. Great talk. I have a million questions written down, so I'll only ask one or two. I'm wondering if you looked at any fully rigidized frames in either titanium or carbon fiber for that comparison in terms of taking out a lot of the moving parts, and or like a full carbon, and or if you've looked at the ethos, which from some patients I've used that with, they very much comfort-wise feel like the vibration is gone. So I'm just curious if there's data and research to support or reject that.
Yeah. I have to say this is an absolutely true story because it really only almost killed Jacob. So, you know that decorative brick? They tore it out over Christmas break. And so he was supposed to come back and do this last chair, and it's now smooth. And I was watching it. I was watching the guys come in and do it. And there's nothing you can do anyway. We got these 4 chairs, right? And so those are the only 4 chairs we got. You know, that's sort of life and research and stuff. I will tell you, we study the ethos in a few different ways because from an engineering perspective, it's quite interesting. And so like we took the stuff out and used mechanical machines and stuff like that. And so, yeah, we did test it. I don't really, and what we did that we did share with Key is sort of how the different colors are in the front and back and stuff like that and what changes they made and their stiffness and stuff. It was kind of cool. I don't really remember results, but you know, that's out of scope, man. Out of scope.
I know you don't have data on like a fully rigidized titanium frame or fully carbon, but just principally, like, would you expect?
Be more. So the more rigid a system, the more it transmits stuff. So, you know, that's why the fat tires don't transmit much stuff. So the argument of rigidity and energy absorption isn't always accurate.
Got it. Thank you.
Rigidity can increase it, or yeah.
No, you're doing good.
As far as the user experience goes, we usually tend to float what comfort means for us. So each one has its own idea about what it's comfortable for them. And in terms of not only you told us the difference between vibration and shock. So it's similar to what he said. It tends to be more like what it feels like and not only the tissue being affected. So which one, maybe like the idea of finding which one it feels, what causes the tiredness? Maybe the vibration on the column, maybe the lumbar section, which feels the vibration or the shock or whatever, but maybe it's not harmful, but which one is more comfortable?
Yeah,
maybe that's the idea.
You know, you're absolutely right, but that's no different than when you test out a bed, right? Or you test out a car seat, or you test out your shoes, right? Or if you're a runner, right? You're sort of doing things, and it's in a very complex situation, right? But it is important. The context is important, right? So if you really want to assess comfort of a wheelchair and vibration, don't do it on carpet. Okay? This room is not how you assess that because there's nothing there. Okay? And that would be the same with a runner, right? I think, you know, they let you go out of the store and go run down the street, right? I guess. The context becomes important. The other caveat is you can pay the price. Some of those components increased propulsion cost. And that is where your trade-off comes into play. How important is this attenuation if you know you're going to have to push and do more work? There's no right or wrong answer, but at least you should be informed of that. That's sort of the point.
Great point. I agree. Do you have time for me? One more question?
Yeah.
And thank you, by the way, for doing this. This is great. there's a famous MIT study in the bike world when it comes to frame geometry and materials. So it contradicts a couple things that are said here, but I was curious. I know apples to apples, wheelchair design, bike design, two different animals, right? I'm wondering, on frame design, it looked like you picked 4 brands, but there was the same configuration of frame geometry. And to that heat or energy that you're talking about, how that dissipates or how that rotates within that, you talked about rigidity.
Mhm.
What was your thoughts on that, and why did you not test all of the frames in that category and really understand that?
The answer to all your questions is money.
Yeah.
Holmeyer, president of NBC Sports.
Yeah, I have one more
No,
too.
he can talk a little about that.
Okay, yeah,
Yeah, so we were we were doing our best to choose representative rigid aluminum frames, carbon fiber frames, titanium frames from the ultra lightweight wheelchair world, right? So yeah, we would love to test every single frame on the market, but each one of those tests takes hours and hours and hours, and students, not just me, the immortal postdoc, but undergrad students too, and grad students. And so we did what we could, right? And
awesome, yeah, I get it. I work for a manufacturer, full disclosure. If you need any product, give me a call. I'll get some over to you. A couple other things too, on the components that you tested, thank God 3 of them are not available anymore,
yeah.
off the market. But did you adjust the chair for those components and the forces that were going into those?
Adjust the wheelchair how? What do you mean by adjust?
So, for example, it looks like you put a knobby tire on there with a 501 rim.
Mhm.
That height of that tire and what that relationship is with that rear seat height and how that reflects to the front of the caster
Yeah, so we
housing.
we
Okay.
did move the axle as necessary to keep the seat height, the seat angle, the frame angles as identical across all the configurations as possible. So
Perfect.
for that mountain wheel, yeah, we did need to adjust the axle slightly, but
And you did answer the question earlier pertaining to titanium and not being able to put that in the equation. But Dr. Sprigle, you mentioned that it would actually create more because of the movement of titanium. I'm just curious.
No, the question was about rigidity, right? If
yeah.
you increase rigidity, if you take away the suspension in a bus seat, it's more rigid, right? And you get
Absolutely.
more vibration. That's why the suspension is there, right? But you're dissipating energy. So I wasn't talking about titanium. The reason we didn't do titanium is because they took away our decorative brick over Christmas. It was very painful.
We
But
have time for one more
so I wasn't
question.
talking about materials, and I'm sorry if I was unclear, but generally, if you want to dissipate vibration, you need to lose energy. And if you don't choose wisely, you're going to end up pushing harder, right? And that is a fat tire bike, but it works on snow. Yeah.
Can I just ask a quick question? I was just going to ask if you studied vibration at the foot plate at all. I know it's not for tissue deformation, but just from a therapist perspective of people with spasticity, the vibration triggering their tone, and then their legs are jumping off the foot plate and they have to stop pushing to get their legs stable and move forward. Was the vibration at that point, not from a tissue damage standpoint, but just to study levels and what could be done to diminish that? Was that studied?
yeah, we did collect data. Not always at the foot plate. It was at the frame right above the caster fork where that attaches to the rest of the frame. So we have data on that, just not enough time in this presentation to go through it all.
Get a bigger cast.